The figure given below shows a fixed pulley used by a boy to lift a load of 200 Newton through a vertical height of 5 meters in 10 seconds. The velocity ratio of the pulley is. So the velocity ratio is the velocity or distance covered. If we take this rope and we pull it down, how much distance it will take by the effort to the distance which this load will move, displacement of the load. So that is the ratio is called velocity ratio. So in this case, it will be same. The velocity ratio will be the same. So it will not change according to how the height is given or time is given. This data is just given to confuse us. Velocity ratio is by design, by geometry. So like on paper, if we are designing this pulley, we will say how much we will pull this rope this side. The same length, the load will go up. So what we are talking, the displacements will be the same. And the velocity ratio is the ratio of displacements. Displacements of effort, we can say dE divided by displacement of load. So in this case, because it is a fixed pulley, this will be the same. That is why, with the velocity ratio will be equal to 1. Now you'll be thinking like here given 240 Newton we are applying and only 200 Newton load is picked up. Will that affect? Force does not affect our design. So this he maybe applying more load because there is a friction here like to overcome that, and that is considered in mechanical advantage where we talk about the forces, how much force we are putting and how much load we are able to put. But that is not in the scope when we are discussing velocity ratio. So remember that. So this all data of this force, 5 meter, 10 second, this was just given to confuse us. So if we stick to the formula, what is velocity ratio, and we focus on what this means and how much it will change or not, then we will understand that velocity ratio will remain same. So the option will be B. Let's see question number 2. The mechanical advantage of an ideal single movable pulley. So this is a movable pulley, so it can move. Is 2, right? So that is like 2. Why? See, if you are putting an effort here, like if you are pulling a load like this, we have a load and you're directly pulling it up by the effort E. So whatever the load is, that much effort you need to put. If you use this kind of a pulley, what will happen is it will be divided in two strands. Now you are supporting, you only have to support half. You just have to put L by 2, L by 2, half of the load. Now you will say that to half of the load, who will support? See that strand, the other second strand that is fixed here with the wall. So L by 2 will be picked by this and L by 2 will be picked by this. That is why there'll be advantage. You just have to, put half the efforts, or your mechanical advantage, you have multiplied your force by 2 times. So effort you put, the load you are able to put is 2 times. That's why the mechanical advantage of ideal pulley will be 2. We'll do this question afterwards. So if there are n movable pulleys with one fixed pulley, the mechanical advantage is given by, this is a generic formula, 2 raised to power n. So if there are one movable pulley, so the mechanical advantage will be 2 into 1. So if there are two movable pulleys, just put n is equal to 2, you will get advantage of 4. Like that, we can understand this. Okay, let's go ahead. Which of the following, let me zoom in it a bit. So what they are asking is they have given detail about single fixed pulley and single movable pulley, and which of the following between single fixed pulley and a single movable pulley is incorrect. So we have to find incorrect. It is very small. So let me zoom in. so that you can see it properly. What are the options? Okay, so let's go. So a single fixed pulley, it is fixed to a rigid support. Yes, that it doesn't move. That's why it is fixed. As movable pulley, it is not fixed to the rigid support. This is also correct. So this difference is correct. The load moves in a direction opposite to the effort. The load moves in the direction of the effort. So if you want to understand, we can put a fixed pulley here. Cross means it can't move. It is connected to the wall. It can't move. Let me put a tackle here. So here is a tackle. Now we want it is to be moved or use a movable pulley. This kind of diagram we can make. Let me put a tackle here and you can pull it from here, right? So my effort is this side. Let me put the load also. Load is, let's say, in the blue color. I'm going here. It's in blue color like this. And here is a load like this. Okay, I'm pulling like this. This is the effort in this case. Okay, so now if you see, read this, that in the fixed pulley, in this case, the load moves in the direction opposite to the effort, right? I'm pulling it downwards because I'm using fixed pulley, I'm downwards, and the load is going up, right? Effort is downwards. So this is also correct. The load moves in a direction of the effort in the case of movable pulley. So this is the movable pulley. So this is the load. If I pull it upwards, this rope upwards, where the load will go, it will also go in the upward direction. The direction will be same. For a fixed pulley, the ideal mechanical advantage is 1. Yes, ideal mechanical advantage is 1 because the speed at which you will be pulling this, the same speed, it will come up. So it will be same. But here it will be different, right? That the ideal mechanical advantage is 1. This is wrong. This cannot happen. Ideal mechanical advantage is 2. Because if we are pulling it like this, the weight will not come with the same speed. It will be lesser. It will be half of the speed. So let me correct this arrow if it is getting confused. So if we are pulling it by, let's say, L length, so this weight will only go up by L by 2. So the ideal mechanical advantage in this case will be 2, right? So we'll be able to, like in the terms of distance, you can understand, you can also understand in terms of load. Like for example, if I'm this weight is W, then I have to only put effort of W by 2. Half of the effort I need to put. That is why I'll be able to multiply my force. I can make it 2 times. That is why the movable pulley will have ideal mechanical advantage of 2, not 1. That's why this statement is wrong. Let's go ahead. Fixed pulley, the ideal velocity ratio is 2. No, it is 1. 1 means velocity ratio when we are talking about the speed, it will come down this effort, the load will go up the same speed. The displacement it is taken here, the same displacement will go up. So this is not true. Its ideal velocity ratio is 1. This is also incorrect. So this difference is also not correct. So this is also wrong. Its velocity ratio is actually 2. So yeah, like mechanical advantage. So what does that mean? So like if we pull it this, then our load will only come half a distance. We have to pull by more length to get it upwards. The fifth, the axis of rotation does not move in the space. Yeah, it is fixed from here. It is attached. That's why it's called fixed. So it will not move. The axis of rotation also moves. Yes, this is the axis of rotation of the pulley. When we are pulling it up, this pulley will also go up. So this axis of rotation also will move. So the wrong options are, here it is number option 4 is wrong, and then option 3 is also wrong. So 3 and 4 are wrong. So this will be our answer, answer D. Let's go next. The relationship between mechanical advantage and velocity ratio for a practical machine is mechanical ratio cannot be equal to velocity ratio because they are talking about practical machines. Practical machines cannot have it. This will hold true in the case of ideal machines. MA can be greater than velocity ratio. This can also not happen. Okay, mechanical advantage can never be according to the VR greater than that. Mechanical advantage is less than VR. Yes, prefer practical machine. This will be true. So answer C will be true. So this is just a summary I have drawn. So the bigger VR can happen, MA can be small. This will happen for the practical machines. If height is same, I want to show that VR is equal to MA. This will happen for ideal, and VR is less and MA is more. This is not practical. This cannot happen. So remember like that. Okay, let's go question number 7. A boy uses a single fixed pulley to lift a load of 50 kgf to some height. Another boy uses a single movable pulley to lift the same load to the same height. Okay, they are moving at the same height. The ratio of two efforts. See, when he's the other person using the fixed pulley, he has to apply the same load. So he has to apply 50 kgf because the single fixed pulley does not give you any advantage. It just changes the direction. So you will have the convenient direction to apply force, but that's it. It is not advantageous. So like this, if you have a load here, so there is no mechanical advantage here. Okay. So whatever you are pulling for, the same load you'll be picked up. So if you want to pull up 50 kgf, you have to apply the same. So uh, this will be 50 kgf. This guy will be applying 50 kgf. Let's see the other one. Uh, the other person is moving with the movable pulley that has mechanical advantage of 2. So you only have to apply force half of it. That is the advantage of movable pulley, single movable. What will be the ratio? Ratio will be 2:1. 2:1. Right? We can solve it like this, 25 into 2, so 2:1. So this will be the ratio. So what is happening in movable pulley? One end is already fixed on the wall, which will share the load. So if 50 kgf is down here, 50, half the load is already attached here, and you have to give support only to 25. That's why it is advantageous. 2 times the load you are able to book. That's why we are saying advantage is 2 times here. How many strands are supporting the load in case of the block and tackle system of 5 pulleys? Generally, how many pulleys we have, that much strands we have. So it will be 5. How many strands are supporting the load in case of block and tackle system of 4 pulleys when effort is in downward direction? 4 again. 4. Okay. So this is the last question. Let's understand this question now. For a system of n pulleys, the weight of the lower block along with the pulley is W. Okay, so there is a weight involved. Generally, what we do is we ignore the weights of these pulleys, but in practical machines, there will be. And in um, block and tackle system, there will be a lower block, and that can have this pulley can have some weight. Now, due to this, what will happen? Let's see. So we'll understand, like you can see, I have drawn here uh, 3 pulley system, block and tackle. So this is the upper block with 2, and this is the lower movable one. So this is supported like this. Now understand. Okay. So if I'm putting a E effort, it'll go same here, E, E, E here. So 3 stands are supporting it. So 3 pulleys, 3 stands. Generally that happens. Okay, now we have a load here which is getting supported. But the problem is we also have this pulley lower block has weight of W. So we have to pick it up also. So this will also act downward. Let us create a diagram, free body diagram like I want to show. So this is the load, say, This is the load. And addition to it, now the pulley has this weight. This pulley will also have weight. So that is also this side. Okay, so this is our W, small w. Okay, and what is upwards? Upwards are these strands, three strands which are supporting it. But how much force they are putting upwards? See, this is the effort E. So it will be 1, 2, 3, 3E. If it is four pulleys, it will be 4E, four efforts. So number of strands, or you can say generally speaking, it will be N into E. I would have for 3 it will be 3, for 4 it will be 4e. So generally when there are n pulleys, we are just putting a general term here, ne. Now we just need to see like the efficiency formula, because they were asking about the expression about the efficiency. See, efficiency is given by mechanical advantage divided by velocity ratio. So velocity ratio is equal to 3 if 3 pulleys are there, and n if n pulleys are there, or n supporting strands of this tackle. Okay, so we can keep it as n. Now think about it. Here, the load and effort is equal to W by W plus L divided by, no, 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 no. This is no, this is, don't go like this. This will confuse you. Ignore this, I'm writing it fresh. So MA is equal to load by effort. Okay, now we know we can put N here. Yeah, 3 pulleys, we can put N here. We know that. Let's see what MA will stand for. So MA will be how much load we are able to pick it up. Okay. So we are giving an effort of E, but how much load we are able to pick? We are only able to pick the load of L. You know? This is like is coming by design. It has a weight. Otherwise, our objective is to pick up this load. Our objective is not to pick this load, right? So our L will be equal to E. Now, if we use this L by E in this formula, put a VR, we will get efficiency is equal to L by NE. Till here, okay? We are able to understand L by NE. The major confusion is here, like what to put L. See, mechanical advantage will see only how much load you are able to pick with the effort. Okay, so this much effort I put, this much load I am able to pick. Okay, so that is a mechanical advantage. So we'll only put L, not L plus W here. Okay, so that is, if that is clear, now we are done. Here load, what we should do, what we can put instead of L here in terms of this. So if this diagram you see, the NE was upwards, 3 strands I'm just showing with 1. See, these 3 forces I'm just combinedly showing by this. So this is NE upwards. So can I say NE is equal to W plus L, right? Downward 2 forces, upwards 1 force. And can I say L is equal to NE minus W? NE minus W is equal to L. Yeah, and we can put this L value here, right? So what will happen now? L will become NE minus W. So NE minus W divided by NE. So what will happen? NE divided by NE minus W by NE. So this will get, we will get this expression. So option A will be the correct option. Okay, let's go next. For efficiency, for greater efficiency of block and tackle pulley system, the lower block should be of negligible weight. Why? Because how less we have to pick extra than load, that is better. Otherwise, if you make this pulley, the lower pulley very heavy, what will happen? We'll end up pulling this also. Then we have to put more effort. That will decrease our efficiency of picking up the load. So that is why we should keep it negligible. Okay, let's go next. So the next is, yeah, the mechanical advantage of class 3 levers is always less than 1. Reason, this is because the effort arm is greater than the load arm. So instead of getting confused, let's draw a class 3 lever. So in class 3 lever, the effort is in between. This is effort and this is our fulcrum. This we can say load. Okay, so this is the scenario. So now see, the effort arm is this much and load arm is this much. So the load arm is more greater than. So what he's saying is reason is giving the mechanical advantage is will be of effort arm divided by this one. ठीक है ना? Effort arm is lesser. So see the mechanical advantage in ideal situation, it is equal to velocity ratio. So it will be, can be understood as effort arm. Effort arm divided by load arm. Okay, so effort arm will be smaller and the load arm will be greater. So this will be like 1 by 3, 2 by 3. The load arm will be bigger. So it will always be less than 1. So this assertion is correct. But the reason they are giving is wrong. This is because the effort arm is greater. No, it's not greater because it is happening because effort arm is shorter. And it is of small as compared to the load arm. That is why the reason is wrong. So the option will be D. Assertion is true, but reason is false.